All right, today we're diving into one of the most fundamental processes in the entire universe, radioactive decay. And it's a fascinating paradox, really. For a single atom, it's completely random, but for a huge group of them, it's incredibly predictable. In this explainer, we're going to unravel that mystery, from the big ideas right down to the math. Let's get into it. So here's our game plan. We'll kick things off with the why. What makes a nucleus unstable in the first place? Then we'll look at the decay curve to visualize it, learn the mathematical language to describe it, and finally, we'll put it all to the test with some real-world problems. Okay, first things first. Why does radioactive decay even happen? Well, it all starts deep inside an atom in what we call an unstable nucleus. At its heart, radioactive decay is just nature's way of finding some peace and quiet. See, an unstable nucleus has way too much energy, and to chill out, it has to get rid of that extra energy by spitting out some radiation. The end goal is always the same, stability. Now, physicists use two really specific words here, random and spontaneous. Spontaneous means you can't force it to happen. You can't heat it up or crush it to make it decay faster. The nucleus just does its thing when it's ready. And random? That means if you have a billion identical nuclei, you have absolutely no idea which one is going to go next. It's this wild combination of unstoppable and unpredictable that makes this whole thing so unique. To really get your head around this randomness, just think about rolling dice. If you toss, say, 1,000 dice onto a table, you're pretty sure that about 1/6 of them will land on a 6, right? But can you point to a specific die beforehand and say, that one's going to be a 6? No way. Impossible. Radioactive decay is exactly like that. We can predict what the group will do, but the individual? A total mystery. And this is where it gets interesting. Even though a single decay is random, what a huge group does is super predictable. And that predictability gives us something we call the decay curve. So here it is, the decay curve. It's a picture of that predictability. You'll notice it's not a straight line, right? It's a curve that gets less steep as time goes on. That's because the rate of decay slows down as there are fewer and fewer nuclei left to decay. This shape is a perfect example of what we call exponential decay. And this curve shows us one of the most important ideas in all of nuclear physics, the half-life. It's simply the time it takes for half of the nuclei in a sample to decay. So after one half-life, you've got 50% left. After a second half-life, you're down to 25%. It's like a perfectly reliable clock for any radioactive element. Okay, now that we've got the concepts down, let's learn the language physicists use to talk about this stuff precisely. Yep, it's time for a little math. First term up is activity, which we represent with a capital A. Think of it like popcorn. The activity isn't how many kernels you have in the bag, it's how many are popping per second. So a higher activity means more pops, or decays, are happening every moment. And how do we measure this activity? We use a unit called the becquerel, or BQ. It's super simple. If a sample has an activity of 100 BQ, that just means 100 of its nuclei are decaying every single second. Easy. Next is the decay constant, this little Greek letter lambda. This goes right back to our dice analogy. It's basically the probability that any one nucleus will decay in a certain amount of time. A big lambda means it's really unstable and likely to decay soon. A tiny lambda means it's pretty stable and will probably be around for a while. And here it is, the physicist's toolkit for radioactive decay. These four equations are the bedrock for everything we're about to do. They connect all the dots: activity, the number of nuclei, the decay constant, half-life, and time. With these, we can figure out the past, present, and future of any radioactive sample. All right, enough with the theory. Let's see how these formulas actually work by tackling some textbook examples. This is where it all starts to click. Okay, problem number 1. We've got francium-221, which has a half-life of 4.8 minutes. The question is, what fraction is left after 14.4 minutes? Well, the first thing to figure out is how many half-lives have gone by. So 14.4 divided by 4.8, that's exactly 3. So the sample has been cut in half 3 times. We just need to calculate 1/2 to the power of 3, which gives us our answer, 1/8. That's all that's left. Nice and simple. Next up, a different kind of problem. This time, we're given the activity and the decay constant for phosphorus-32. We have to figure out how many actual radioactive nuclei are in the sample. For this one, we grab our first tool, A equals lambda n. We just need to rearrange it to solve for n. Then it's just a matter of plugging in the numbers.
5 million becquerels divided by that tiny decay constant, and boom, we find out the sample contains a staggering 8.9 trillion phosphorus-32 nuclei.
Okay, time for the big one, the full exponential decay formula. We're starting with a known amount of phosphorus-32, and we want to know how much is left after 10 days have passed.
Now wait, before we start plugging in numbers, here is a massive pro tip. Always, always check your units. Our decay constant, lambda, is in per day, and our time is in days. Perfect, they match. We're good to go. If they didn't, we'd have to do a conversion first.
So we just substitute our initial number of nuclei, the decay constant, and the time into our equation. Punch that into the calculator, and we see that after 10 days, about 5.3 trillion of those original nuclei are still there, undecayed.
For our last worked example, we're going to flip it around. This time, we have the decay constant for radium-226, and we need to find its half-life, specifically in years.
First, we use our half-life formula. Now, since lambda is in per second, our answer is going to pop out in seconds. A massive 48.8 billion of them. But the question wants the answer in years, so we just have to do one final conversion. And there we go. The half-life of radium-226 is about 1,550 years. I mean, that just shows you the incredible range we're talking about, from a few minutes for francium to over a millennium for radium. All right, you've seen how it's done, now it's your turn. Let's move on to some practice problems to really make sure this stuff sticks. Now, read this one carefully. It's a classic trick question they love to put on exams. We want to know the fraction that has decayed, not the fraction that's left. Okay, so the process starts the same way. 3,200 years is exactly 2 half-lives. So the fraction that's remaining is 1/2 squared, which is a quarter, or 0.25. But that's not what the question asked. It wants the fraction that's decayed. To get that, we just subtract what's left from the original whole. So 1 minus 0.25 gives us our real answer. 0.75, or 75% of the sample, has decayed. Here's another common type of problem. We know the activity of this radium-222 sample drops from 350 down to 210 becquerels. The question is, how long did that take? For this, we have to do a little bit of algebra and rearrange our main decay formula using natural logs to solve for t. Once we have that, we plug in our values, which gives us a time in seconds, and then we just convert that to days. And we get our final answer about 2.9 days. Okay, let's wrap this up with one final challenge, pulled straight from an old exam paper. This will test if you can put all the pieces together when it really counts. So here it is. Half-life is 20 days. We wait 60 days. The key here is recognizing that 60 days is exactly 3 half-lives. So the amount remaining is the initial number halved 3 times, which gets us down to 1 times 10 to the 10. But again, the question asks how many have decayed, so we subtract what's left from what we started with.
Which gives us our answer, D, 7 times 10 to the 10th, a classic 2-step problem.
So after all of that math and all those examples, let's just take a step back and end with the most fundamental question of all. What do we really mean when we talk about radioactive decay?
It's this incredible natural process where an unstable nucleus finally gets a chance to relax by releasing some energy. It's totally random for any single atom, but beautifully predictable when you have a whole bunch of them. And that predictability, that reliable ticking clock of the half-life, is what allows us to date ancient artifacts, track medical treatments, and even power our cities. It's a journey from pure chaos to perfect order. Thanks for joining me.